Hi there. So for this first part of the question, y equals 3x to the power 4 minus 8x cubed minus 3, we're asked to find dy by dx. So therefore, if we differentiate this in the usual way, dy by dx, for terms like this, remember, you just have to multiply the power by the number in front of the x. So you got 4 times 3 is 12, so you're going to get 12. Then you reduce the power by 1. So if we take off 1 from the power, that's going to give us 12x to the power 3, 12x cubed. Similarly, for this next term, minus 8 times 3 is going to be minus 24. Reduce the power by 1, so that's going to give us x to the power 2. So we get minus 24x squared. And for the constant, remember that constants differentiate to 0. So dy by dx then, 12x cubed minus 24x squared. Hi. Now for the second part then, we have got to find d2y by dx squared, and in the previous part we got dy by dx, so we just need to differentiate dy by dx with respect to x again, and that will give us d2y by dx squared. And if we do that, again for terms like this, you just do 3 times the 12, which is 36, and then you drop the power by 1, so it's going to be 36x squared. For the next term, minus 24 times 2 is minus 48. Drop the power by 1 and you've got minus 48x, x to the power 1, okay? And there's d2y by dx squared. Hi. So for this part, if we're to verify that the curve C has a stationary point when x is 2, what we need to do is substitute x equals 2 into dy by dx, which gives us the gradient. And remember that when you've got a stationary point, you would expect the gradient to be 0. So when x equals 2, I'm hoping this will come out to 0. So we'll just put this down, that when x equals 2, the gradient, which is given by dy by dx, if we substitute 2 in, we've got 12 times 2 cubed. I'll just show the working, okay? Minus the 24 times 2 squared. And we can see that what we get here is 2 cubed is 8, 12 eighths, 96. And then we've got 2 squared is 4, and then 24 times 4 is 96. So we end up with minus another 96, and that gives us 0. Okay, so therefore, I think we should conclude that therefore a stationary point, rather than just leaving it at 0. Therefore, a stationary point when x equals 2. Okay, and there we go. Hi. Now, when it comes to this part C, where we've got to determine the nature of the stationary point, giving a reason for our answer, we've got two options. We can either go for the quickest method, in my opinion, for this question, which is to substitute x equals 2 into d2y by dx squared, and check to see whether we get a positive value, in which case it will be a minimum, or if we get a negative value, it will be a maximum. But if we get 0, it will be inconclusive and we'll need to take it further, okay? Or the other way is to do a gradient table and check it out there. I'll show you both methods, okay? So if we decided just to substitute x equals 2 into d2y by dx squared, let's just do that method and check for the sign that we get. Let's put here that when x equals 2, we'll put therefore d2y by dx squared equals, and if we do that, we've got 36 times 2 squared minus 48 times 2. And if you work this out, 36 times 4 minus 96 here the total comes out to be 48, which is clearly greater than 0. So what we've got then is therefore a minimum. Okay, so a minimum, okay, at x equals 2. So that's one way of doing it. The other way is by looking at a table of the gradients. And if I was doing a table, let's just say we draw it up something like this. I would take my points x. We know that it's got a stationary point when x equals 2. I'll take a point to the left and a point to the right. So let's say we take x equals 1 and x equals 3. I'd look at the gradient given by dy by dx, and then I would look at the slope. Let's just put it down here. So we know that when x equals 2, dy by dx is 0, so therefore as far as the slope goes on the curve, the tangent would be horizontal. If I have x equals 1 and I substitute it into here, I'm going to end up with 12 minus 24, which is going to be negative value. Negative 12. I'll just put negative there, okay? And then if we substitute x equals 3 into here for dy dx, you get 108, a positive value. So when it comes to looking at the slope, the gradient, you can see that on the left we've got a negative gradient, which means it's going to be going downwards, the curve, and then on the right of x equals 2 at x equals 3 you've got a positive slope, a positive gradient, which is going to go up something like that. So as far as the curve goes, it's going to be a curve that sits in here, something like that. Not well drawn, but hopefully it gets you the idea that what we have got is a minimum. So if I was concluding this one, I would obviously say a minimum, okay, at x equals 2. So I hope that's given you some idea then on how to do that part. Hi there. Now for this question you're asked to find the length of OD, and in order to do this you should be familiar with the formula here for the length of the arc of a sector. If not, just a quick reminder that the length of an arc of a sector when theta is in radians is a fraction of the circumference. That's theta over 2 pi is the fraction and the circumference is 2 pi r. The pi's cancel, just leaving you with the length being theta r. So in order to do this, we know the length of the arc L, it's 3 centimeters, and we know the angle theta is 0.4. So it's a question of just rearranging that. So we know then that using that formula that 3 must be equal to theta, that's 0.4 times the radius r, or we might as well call it OD. And so rearranging that, we've therefore got that OD equals 3 divided by 0.4. And if you work that out in your calculator, you'll find that you get 7.5. So 7.5 and the units will be centimeters. Okay? Hi there. Now for this question, we're asked to work out the area of this sector AOB. And in order to do that, you've got to be familiar with the area of a sector formula when the angle theta is given in radians. And that formula, remember, was a fraction, theta over 2 pi, of the area of a complete circle, pi r squared. The pi's cancel, leaving you with the formula that the area is a half r squared theta. So we don't know the radius, we don't know the angle theta yet. We can work out the radius, distance AO, quite easily because we already have worked out the length OD in the previous part of the question. We found that to be 7.5 centimeters. So to get the length AO, it's just a simple case of 12 centimeters minus the 7.5 centimeters. And if you do that, we end up with 4.5 centimeters. So that's the radius. Now we need to get this angle AOD, and that's easy as well because we should be familiar with half a turn, that's pi radians. We've got the angle here of 0.4, so therefore we've just got to take that away from pi radians. So we've also got the angle AOB. In radians, that's going to be pi minus 0.4. And if you do that on your calculator, you should end up with 2.7415 and so on. Okay, and that'll be measured in radians. You can either write the word radians or you could use the symbol C. Now, we've got that, so we're in a position to work out the area of the sector. So I'll just put a little intro here. Area of sector, and that's the sector AOB. And if we pick up then on this formula here, it's going to be a half times the radius squared, which is 4.5 squared, and then we have got times the angle, and the angle we've just seen is 2.7415 and so on radians. You don't need your calculator in radians mode, okay? You can just work it out in a normal mode. And if you do that, you should find you get 27.758 and so on. And if we were to give this, say, to 3 significant figures, then it would be 27.8. And the units would be centimetre squares. And we'll just say that that's to 3 significant figures. Okay. Hi there. Now for this question, we were given the equation of the circle C as being this equation here and asked to find the coordinates of the centre of the circle. Well, just as a reminder, if you have an equation of a circle in this format here, then the centre has coordinates AB and R is the radius. So what we need to do is make this equation have this form here. And we do that by completing the square over the x terms and the y terms. So if we look at x squared minus 4x first of all and complete the square on that, we'd take the x and we'd halve the coefficient of x. So halving the minus 4 gives us minus 2, and then we square that. If you were to expand this bracket, you'd get x squared minus 4x, but then the minus 2 when you square it is plus 4, so we subtract that 4 away. So that would give me just the x squared minus 4x. Now for y squared plus 10y, we do that in a similar way. We put a y here and we halve the coefficient of the 10, so that's going to be plus 5, and then we square it. And if you were to expand this bracket here, you'd get the y squared, you'd get a couple of 5y's, which would give us 10y, but you'd get 5 squared, which is 25. So we need to subtract it. And so that together would just give us y squared plus 10y, okay? And then that equals the constant k on the end. And if we simplify this, that would be x minus 2 all squared, plus then the y plus 5 all squared, and we've got minus 4 minus 25, which is minus 29. Add that to both sides, that will give us k plus 29. And comparing this with what we see here, then you can see that A is going to be the 2 and B would correspond to minus 5. So therefore we have a centre of the circle. Just put the intro here. Centre at 2 minus 5. Okay. Hi. Now for the last part of this question then, we're asked to state the range of possible values for k. Well, we've seen that the equation of the circle can be expressed in this form, and k plus 29 represents the radius of the circle squared. So clearly it's this radius squared which has to be a positive value. It has to be greater than 0. So what we've got is r squared equals k plus 29, and that must be greater than 0. So therefore, if I subtract 29 from both sides, we can see that k must be greater than minus 29. And that gives us our range of possible values for k. Okay? Hi. So for this question then, we were given this integral and it was equal to natural log of 7 and asked to express a in terms of the natural log of k. So where k was a value to be found. So in order to do this, what I would want to do then is just evaluate this integral obviously first, and I'd divide both of these two top terms by t. So what we've got then is the integral going from a to 2a of t divided by t, which is 1, and then plus 1 divided by t, 1 over t. Don't forget we've got a couple of terms here, so we need to put that in brackets, and we're integrating it all with respect to t. So we can integrate each of these terms. The integral of 1 is just going to be t, and the integral of 1 over t, well, that's going to be the natural log of t. We don't need to put this in mod signs because we're told that a is going to be a positive constant. So that would mean that the t is also going to be positive when it comes to substituting values of a into here. Remember, the limits go from a to 2a. So if we substitute our values in, 2a first, we're going to have 2a here, and then plus the natural log of 2a, and then we would subtract what we get when we substitute the a in. So we're going to have a plus the natural log of a. And then cleaning this up, we're going to have 2a minus the a, which is going to leave us with a, and then you've got the natural log of 2a minus the natural log of a. So that's going to be, by the subtraction rule of logs, the same as the natural log of 2a divided by a. Okay, so I hope you're familiar with that rule. The a's cancel, and that just leaves us with the natural log of 2 there. So if we just come down here, now we can finish this off. We've therefore got the natural log of 7 here on the left hand side equals a plus the natural log of 2, and then all I've got to do is subtract the natural log of 2 from both sides, and that will give us a as being the natural log of 7 minus the natural log of 2. And again, we can use the subtraction rule here for logs, and that's going to be the natural log of 7 over 2. Now, this is identical to the form we had to show for a, and that's the natural log of a constant k. So we can just say that where k is equal to 7 over 2. And there you go. Hi there. So for this question then, we were given the parametric equations here and asked to find the Cartesian equation for the curve in the form y equals some function of x. So in order to do this, what I need to do is eliminate t between these two equations. So I'm going to number the two equations for reference as 1 and 2. And I think the easiest one obviously to work with is this equation 1 here. So if we make t the subject from that first equation, then if I add 1 to both sides, divide by 2, then I'm going to get t equaling x plus 1 all divided by 2. So we've got that. I'll call that 3. And then what I'm going to do is substitute 3 into 2. Okay? And doing that, what we've got then is therefore y equals 4 times t, so 4 times all of x plus 1 over 2, and then we've got the minus 7, and then plus 3 divided by all of t. So that's going to be x plus 1 over 2 there. So I need to clean this up. For this term here, I can multiply top and bottom by 2. So if I do that, and also I can clean up this first term here, I can see that that 2 goes into that 4 there twice. So what we've got then, if I expand the bracket at the same time, is you've got 2 times x, that's 2x, 2 times 1, that's 2, and then you've got the minus 7, and as I said earlier, if you times top and bottom here by 2, you've got 3 times 2, which is 6, and that's going to be all over x plus 1. Okay, let's just work our way down this side here. So what I would want to do now is just tidy this up. I'm going to put it all over a lowest common multiple of x plus 1. So we've got y equals, and then we'll have that denominator there as x plus 1. So I've got 2 minus 7, that's going to be minus 5, and so I would have 2x minus 5, and I'm going to multiply that then with the x plus 1. So I'll put that in brackets, 2x minus 5, and that's multiplied with the x plus 1. So that term there would just leave me with 2x minus 5, because those two x plus 1s would cancel. Okay, so that takes care of that. And we've got the plus 6 now that's left, and that would be over x plus 1. So just need to expand the bracket here. So if we do that, we've got 2x times x, which is 2x squared. And then you've got 2x times 1, that's 2x, minus 5x, that's going to leave me with minus 3x. And then you have got minus 5 times the 1 is minus 5. Plus the 6, that's going to be plus 1. Okay, and that's all over x plus 1. And now I can see that this is in the form that we were asked to give. That form, remember then, was 2x squared plus ax plus b all over x plus 1. And we had to give it in this form, stating the values of a and b. So I'm just going to finish by saying where a clearly is equal to the minus 3 here, and the b is equal to 1. Okay, so there we go. All right. Hi, so for this part of the question, we are asked to estimate the volume of oil then that will be extracted after 3 years of drilling using this model here. Well, the first thing I'd want to do is work out how much it's going down per year. And you can see that it's dropped from 16,000 to 9,000 barrels in 4 years. So that's a drop of 7,000 over those 4 years. And then all we need to do is just divide 7,000 by 4, and that will give me how much the rate of decrease is per year. So that'd be 7,000 then divided by 4. And if you do that, you'll find that you get 1,750, and that's barrels. Okay, so just put that in there. So when it comes to working out the volume after 3 years, all I need to do is do 16,000 minus 1,750 times 3. Okay, so we'll just put an intro there just to finish it off. We can just say volume after 3 years, and what we've got then is 16,000, that's the initial bit, minus 3 years at 1,750. Work that out and what you end up with is 10,750. Okay, and that'll be barrels. Hi. Now for this question we are asked to give a limitation for model A, and you can see that the volume here becomes negative when the graph goes below this horizontal axis, the time axis. So the volume will become negative as t gets larger, and you can't have a negative volume. Okay? Hi. Now for this part of the question then, we're told to assume then that model B follows an exponential model. And we've got to find a possible equation then for that curve here. Well, it's going to take on the form V equals. Now an exponential model is going to have the form e to the power kt. Now because it's decreasing, I would expect this constant k to be negative. We've also got a constant that we ought to put in the front here for where it crosses the vertical axis, the v-axis. So I'm going to call that constant a, and that will be a positive constant. So using the information, the coordinates that I've got here, I should be able to work out what the constants a and k are. Okay, so that's the method. So let's just go ahead now and use that model and work this out. So I've let V then equal AE to the power KT, where K is going to be a negative constant and A will be a positive constant. We know that when T is equal to 0, then the curve crossed the V-axis at 16,000, and we can then substitute this in, and what we get is 16,000 here, okay, equals the constant a e to the power k times 0. Well, that's just going to be 0, and e to the power 0 is 1, so that means that we've therefore got a equaling 16,000. Right, so let's move on, and we need to work out k, and we can do this by looking at the other coordinate. That is, when t equals 4, we know that v equaled 9,000. And if we substitute that in to our equation, we've got 9,000 then for v equals 16,000, which we've got for a, and then it'll be e to the power kt. That'd be k times 4. I'm going to write it though as 4k, it looks better. And then if I rearrange this, I've got e to the power 4k equals 9,000 divided by 16,000. Well, that's going to be 9/16. Okay, so let's just come down this column here. And if we do that, carrying on, we've therefore got that 4k, if we take natural logs to both sides, we get 4k equals the natural log then of 9/16. Now, I'll divide both sides by 4, and we end up with k equaling 1/4 of the natural log of 9/16. Now I could leave it like that as an exact value, that's up to you. If you do carry on and work it out on your calculator, you'll indeed see that k turns out to be a negative value, as we would expect. It's minus 0.1438 and so on, okay? Which, if you round it, say, to 3 significant figures, is going to be minus 0.1442 SF, 3 significant figures for short. So therefore our equation, our exponential curve has the equation 16,000 then times e to the minus 0.144t. Okay? You could either put in the decimal here or you could write in the exact value. That's up to you. Okay? Hi. So for the last part of this question then, we use the model that we found in the previous part of the question, which you can see I've given as either two versions here. You can have this version, or you can have the exact value of k here, 1/4 natural log of 9/16, which as decimal is minus 0.1438 and so on. So if we're to find the volume after 3 years, it's just a simple case of substituting t equals 3 into either one of these equations. And to save time, if you've done that, this is what you should see. That when t equals 3, substituted in, I've substituted in the first equation here, you end up with 10,392.30 and so on. Okay. Well, I've rounded this to the nearest 100 barrels, and that's 10,400. Okay. Hi. Now for this question then, we were given this triangle ABC and the two vectors AB and BC, which you can see I've drawn on here as column vectors. Now we've got to find then this angle BAC here in degrees. And in order to do this, what I'm going to do is use the cosine rule. To use the cosine rule, I need to know the lengths of all three sides. Well, I can easily get the length of AB and the length of BC by working out the magnitude of these two vectors. I can get the length of AC by combining the two vectors AB and BC, getting the vector AC, and then going on to work its magnitude out. So I'll have the lengths, the magnitudes then of all three sides, and I use the cosine rule. Okay, so that's the method behind this. So let's get cracking then. I'll just draw a line down here, and the magnitude of any vector, okay, in this case then we're going to be looking at AB. Just put that in the magnitude signs. Remember, all we need to do is essentially use Pythagoras' theorem. It's the sum of the squares of the components. So that's going to be 2 squared plus 3 squared plus 1 squared. And if you work that out, it's going to be equal to the square root of 14. And I'm going to just leave it as an exact value. If we do much the same again for BC, work out the magnitude of the vector BC, then that's going to be the square root then of the sum of the squares here, and it'll be 1 squared plus 9 squared plus 3 squared. Remember, you don't need to put the negative 9 here, all squared. So if you do that, you'll end up with the square root of 91. Now we need to get the magnitude then of AC, and first of all then we need to get the vector AC. So I can get the vector AC very easily just by combining by vector addition the vector AB added to the vector BC. Okay, so if we do that, I'm just going to write them out as column vectors because I think that's quicker and easier. 2, 3, 1 plus the vector 1 minus 9, 3. And doing that gives us the vector 2 plus 1, that's going to be 3. We just add the components. 3 plus minus 9 is minus 6, and 1 plus 3 is 4. So we've got that vector AC. All I need to do now is get the magnitude of it, so we can come underneath here and say therefore the magnitude of the vector AC, again by Pythagoras' theorem, is going to be the square root of the sum of those squares of the components. So 3 squared plus 6 squared plus 4 squared. Again, we don't need that negative in here. Work this out and you've got the square root of 61. So now we've got the lengths of all three sides. I can turn to the cosine rule. And I'm assuming that you're familiar with finding an angle using the cosine rule. In this case, the cosine of the angle BAC, let's just put it in here, the angle BAC. By using the cosine rule, remember it's equal to the sum of the squares of the lengths of the two sides that surround the angle. So that'd be AB squared plus AC squared. Well, if I square AB, that's going to be 14 plus the side AC. When you square it, that's going to be root 61 squared, so that's going to be 61. And then you subtract the side opposite the angle that you're trying to find. So that would be the length BC. If we square the length BC, it's going to be 91. And then it's all divided by twice the product of the lengths of the two sides that surround the angle. In other words, AB times AC. Length of AB then is root 14 and the length of AC is root 61. So we just put those in. We need to work this out in degrees, so you need to make sure your calculator is in degrees mode. If you do that calculation, you should find you get negative 0.2737 and so on. Okay, leave it up to you to check that out. Then to get the angle itself, the angle BAC, just take the inverse cosine to both sides and you should find that you get 105.88 and so on. Okay, that'd be measured in degrees, and if we give this to one decimal place as asked, that's going to be 105.9 degrees to 1 dp for short. Okay, so I hope you got that. Hi there. So in order to show that f of x equals 0 has a root alpha in the interval 3.5 to 4, what we do is we use the change of sign method. So we put in x equals 3.5 into here and x equals 4, work out whether we have got a change in sign, which would indicate that the curve crosses the x-axis on the assumption that this is continuous over that interval. So that's the method. All we need to do then is just carry it out. So if you let x equal 3.5, you should find that f of 3.5 turns out to be minus 4.80 and so on, a negative value. So what I'm hoping for next is that when we put x equals 4 in, we will get a positive value. So if you do f of 4, okay, you do in fact get a positive value, 3.09 and so on. So if you were to sketch the graph, not that you have to, but what we've got here is that for 3.5 you can see would have a negative value, and when x is 4 you'd have a positive value. So assuming there's no breaks in the curve, it's continuous over this interval, then there must be a root alpha in that interval. So you would sum this up by saying something along the lines that since there is a change in sign then over the interval 3.5 to 4 and f of x is continuous over the interval, then f of x has a root alpha in this interval. Okay? Hi there. So for this part of the question then, we've got to use the Newton-Raphson procedure to obtain a second approximation for alpha. So you should be familiar with this formula here. If not, do go back and check out my tutorials on the Newton-Raphson method. So to save us time, we're lucky that they give us the initial value, which is x1, which is 4, and they give us the values for f of 4 and f dash of 4 just jot them down again here. F of 4 then is 3.099, and f dash 4, that's the first differential of f of x. When we substitute x equals 4 in, is 16.67. So to get x2, all we do is set n here equal to 1. So x2 is going to equal x1, the first approximation, minus f of 4, okay, all divided by f dash of 4. So substitute those values in, and you should find that your approximation for alpha takes on this sum here. And if you work that out, you find you get 3.8140 and so on, which rounded to 3 significant figures is 3.81 as requested. Okay? Hi. Now for this part, what we're asked to do is show that f of x equals 0 only has one root. That is where this graph, if you were to draw it, would cross the x-axis. It will cross the x-axis in only one point for x greater than 2.5. So how are we going to do this question? Well, for something like this, not that you have to draw this, but the concept is that if you had the graph of f of x, you would expect it to cross the x-axis only once. And we can test this by checking to see what the gradient is. That is by differentiating it, f dash x. And if it's positive, we would be guaranteed that that graph would cross the x-axis in only one place. That would be our root there. Or it might be decreasing. F dash x is negative. It's coming down and only crosses the x-axis in one point. So we need to test for the sign of f dash x to see whether it's positive or negative. So I'll just remove those graphs, and we'll start then by differentiating f of x. So therefore we've got f dash of x, and the first term we have to differentiate is the natural log of 2x minus 5. And to differentiate that, we need to use the chain rule, which you should already be familiar with. So if I was differentiating this, normally it'd be expected to do it in my head. But if you did want to show working, it would look something like this. So I'm thinking y equals the natural log of 2x minus 5, and I would let t equal 2x minus 5. So dy by dt would be the differential of the natural log of t, which is 1 over t, and that would be now 1 divided by what t stood for, which is 2x minus 5. And then we need to multiply this with the differential of t, which was the 2x minus 5, and if you differentiate that, you'll get 2. So it'll be 1 over 2x minus 5 multiplied by 2, which will give us 2 then over 2x minus 5. And then if I differentiate the 2x squared, well, that's going to be 4x. Differentiate the constant here, minus 30, well, that goes to 0. So we've got f dash of x. Now we just need to see whether this is always going to be positive or negative for x greater than 2.5. Well, let's just put down here that since x is greater than 2.5, then looking at the 2x minus 5 here, we've got that therefore 2x minus 5 must clearly be positive. It must be greater than 0 because 2 lots of 2.5 is 5. 5 take away 5 will give us 0, but if x is more than 2.5, then clearly this is going to be greater than 0. And for the term 4x, we'll just put here, and we've got 4x, well, 4 times any number greater than 2.5 is clearly also going to be positive. Okay, so therefore we can see that we're adding together two positive values. So f dash of x must be greater than 0, positive. So therefore we know that there is only one root. Okay, and I'll just put that in there, only one root. So there we go. Hope you've been able to get that. Hi there. Now for this part of the question, we're asked to prove this identity. Tan theta plus cot theta is identical to 2 cosec 2 theta. So like any identities, when you have to prove them, you've got to decide which side you're going to start with. And it doesn't really matter, but you would normally start with what you would think is the easiest side, and I think it's the left-hand side. We've got 2 terms on the left-hand side, and I'm heading towards 1 term on the right-hand side. Normally easier to reduce terms, I feel, down to fewer terms. So that's what I'm going to start with, and that is the left-hand side. So I'll put that down as proof, and I'd copy the left-hand side down. Or you could write LHS for short. Okay, so I need to think about where this is going. And I get a few clues from the right-hand side here. Let me just jot down what I think the clues are. Cosec of 2 theta. What's that identical to? Well, it's identical to 1 over sine 2 theta. All right, cosec of any function is 1 over the sine of that function. So it's 2 theta in this case. Now, what is sine 2 theta? You should be familiar with that. It's identical to 2 sine theta cosine theta. So this is now starting to give me an idea where this is going to be going. I need to convert this into sines and cosines. I know that cot theta is 1 over tan theta, but I don't really want to keep this in terms of tan theta. I need a mix of sine theta and cosine theta. So let's just put this down here, that this is identical then to, well, for tan theta, that's sine theta divided by the cosine of theta. And then we've got plus cot theta, which is, 1 over tan theta, but that's the same as cosine theta over sine theta. So you can see I'm getting this mixture now of sines and cosines as we want to head towards over here. Right, I've got 2 terms now, and I need to reduce it to 1 term. So that gives me another clue, and that is to put this all over 1 lowest common multiple of the denominator here. And that lowest common multiple is going to be cosine theta sine theta. And so if I take this first fraction, I can see that I multiply the denominator here by sine theta, so I must do the same to the top. So sine theta times another sine theta is sine squared theta. For this fraction here, I multiply the denominator sine theta by cosine theta. So I need to multiply the top of the fraction by cosine theta. So cosine theta times another cosine theta is cos squared theta. Now I should be able to recognize the top here of the fraction. It's a well-known identity. Sine squared of an angle plus cos squared of the same angle is always 1. So I've got 1 then over cosine theta sine theta. And look how this is shaping up to this. The thing is, I haven't got a 2 in the denominator here, but if I multiply top and bottom by 2, it's going to be still the same fraction. Okay, have the same value. 2 over 2 is 1, so I'm not changing the value of it. But what I end up with now is 2 on the top, okay, over 2 cos theta sine theta, and 2 cos theta sine theta is the same as sine 2 theta. So I've got 2 over sine 2 theta. And as we've seen, 1 over sine 2 theta is cosec 2 theta. So this is identical to 2 cosec of 2 theta. All right, so hope you've been able to get that. Hi. Now for this part of the question then, we were asked to show that this equation, tan theta plus cot theta equaling 1, does not have any real solutions. Well, what we need to do is draw from the first part of the question where we took the left-hand side, tan theta plus cot theta. We saw that it was identical to 2 cosec 2 theta. So if that's the case, then from the previous part, we've got 2 cosec of 2 theta must be equal to 1. Now, the cosec of 2 theta is the same as 1 over sine 2 theta. So this is exactly the same then as 2 over sine 2 theta. And this would have to equal 1. And if I multiply both sides by sine 2 theta, I end up with therefore sine 2 theta equaling 2. Now, should be familiar with the sine graph. If we were to sketch that graph, it would look something like this. The graph only goes between -1 and 1. So therefore, we wouldn't expect the sine of any angle to be equal to 2. It's outside the range. So therefore, we can conclude there that there must be no real solutions, since sine 2 theta only goes between -1 and 1. Okay, so hope you've got that, and thanks for watching. Hi there. Now in this video what I want to do is show you how we can take y equals sine theta and differentiate it from first principles and get the result that dy d theta is equal to cosine theta. Now what I'm going to be assuming throughout this video though is that you're familiar with this identity, the sine of a plus b, and also this result about limits where h is an angle that tends to 0. So let's start then. What we do is we increase the angle theta by a small amount, let's say delta theta. So what we have here is the sine now of the angle theta plus a little tiny amount, okay, delta theta. And what's going to happen is that y is going to increase by a small amount, let's say by delta y. So we've therefore got y plus delta y equals the sine of all of theta plus delta theta. Next, what I'm going to do is subtract y from both sides. So therefore we have delta y equals the sine then of all of theta plus delta theta minus y. And the next stage is to work with the identity up here. I'm going to expand the sine of theta plus delta theta, replacing the a with theta and the b with delta theta. So as I say, you should be familiar with that identity, and that will give us the sine then of theta cosine of delta theta plus the cosine then of theta sine delta theta. And then we've got the minus y here. But I'm going to replace that y then with sine theta. So we have minus sine of theta. And the next thing I'm going to do is factorize the first term here and the last term here by pulling out sine theta as a common factor between both of them. So we end up with sine theta times all of cosine delta theta, and then I've got minus 1, all right, for that term there. And then we'll just put that term down plus the cosine then of theta sine delta theta. The next thing I'm going to do is divide both sides by delta theta. So I get delta y divided by delta theta is equal to this term here divided by delta theta. I can write it all over delta theta, but it's exactly the same result if I just put that part over delta theta. You'll see why in a moment. And then for this term, dividing it all by delta theta is just the same as dividing that factor in there by delta theta. Okay? Now, as we let delta theta tend to 0, then what happens is that delta y over delta theta tends to a limit, which we call dy by d theta. And we can pick up on this result here, which I'm taking as assumed knowledge. If we have h, a small angle, tending to 0, then sine h over h tends to 1, and the cosine of h minus 1 over h tends to 0. I haven't got h here though, I've got delta theta instead. So that would translate to this result, that the cosine of delta theta minus 1 over delta theta tends to 0, and the sine of delta theta over delta theta tends to 1. So I can substitute these results into here and here. So what we've got here is this tends to 0, and sine theta multiplied with 0 is 0. And this result here is 1, so cosine theta times 1 is cosine theta. So therefore what we've got is that dy by d theta is equal to cosine of theta. So you can see that by differentiating sine theta with respect to theta, the result then is cosine theta. Okay, well I hope you're able to follow that, and thanks for watching. Okay, for this part of the question then, we're given this equation, gives us the height of the arrow at a distance d from the archer. It might help just to show a diagram of this actually. So I've got one here where we've got the distance d when it equals 0. That comes out at 1.8, and that's got to represent that the height that the arrow was initially fired at. Now if we're going to find out the distance when the arrow hits the ground here, that's going to be when h equals 0. So it's just a question of solving this equation for when h equals 0. So if we put in when h is 0, that's when it hits the ground, you can solve this quadratic equation. Now I don't fancy trying to factorize this, so what I'm going to use is the quadratic formula. I don't like the fact that it starts with a negative here, so I'm going to multiply throughout by -1. And if we do that, we get this line here. So I can use the quadratic formula with a being 0.002, b being minus 0.4, and c being the -1.8. And if you use the quadratic formula, you'll get this line here. And solving this, if we take the positive value, you'll find you get 204.403, and the negative value gives us minus 4.403. Well, clearly it can't be the negative value because we're told that d is greater than or equal to 0. So it's got to be this answer, and if we round that to 3 significant figures, it's going to be 204 meters. And in part B, what's the significance of this 1.8? Well, I've already mentioned it here really. It represents the height from which the arrow was initially released. Okay? Okay, so for this question then, we're asked to write this expression in this particular form. So what we've got to do is complete the square for an expression like this. Now, because this term here, the d squared term, is negative, it's a good idea to pull out minus 0.02 as a common factor first of all. So if we do that, what you're going to get is this line here. Now, we've got the d squared minus 200d minus 900 in the bracket here, which is in the right form for completing the square. So what I'd want to do now is say that this is identical to the minus 0.002 that we have. And then in the usual way, when you get an expression like this, we just set up a bracket. In this case, it's the d. And then we halve the coefficient of d, which is half of minus 200 is minus 100. Put that in there, close the bracket and square it. When you square this out, you're going to get d squared minus 200d plus the result of minus 100 squared. That's going to be plus 10,000. So we've got to subtract that 10,000. Okay, so we subtract the 10,000. This, if you worked it out now, will just give me d squared minus 200d. And then I just tag on the end the minus 900. Okay, so we've got that line there. It's just a question now of simplifying this. And if you multiply minus 0.002 with minus 10,900, you'll end up with this 21.8, and then you've got minus 0.02 times the d minus 100 all squared. Okay, so you can see it's in this form here. So I'll just take that away and we can write that it's identical then to a minus b all times d minus c squared, where a is 21.8, b is 0.02 and c is 100. Okay? Okay, for this part of the question then, we're given this new expression for the height h. And it says hence, so it's obviously got to be related to what we worked out previously. Well, the previous archer had his height for the arrow given by this expression. And we can see that when we compare the two, that this is 0.3 more than the 1.8 here, going up to the 2.1. So we saw that this first expression was equal to this when we completed the square. So all I've got to do is just add 0.3 to the 21.8. And if we do that, we end up with the 0.3 added to the 21.8, and it gives us 22.1 then, minus what we had before. And in this form, it makes it very easy to be able to determine the maximum height. That maximum height is going to be when this term here goes to 0. That's when d is equal to 100. So if we just put that in, we can see the maximum height occurs when d equals 100. It will make this term here 0. So therefore, the maximum height's got to be 22.1. And that's the answer to D part 1. And it occurs at a distance of 100 meters from where it was fired. And that's the answer to D part 2. Okay? Okay, for this question then, we were given that n equals a times t to the power b and asked to show that we could express it in this form here. Now to do this, we need to take logs to both sides. I can see that just basically because we've got the log here and the log being used over this side. So take logs to base 10 to both sides and you should find that you've got something like this. Next, I'm going to look at this term here, the a times t to the power b. Remember, it's just the t that's raised to the power b, and I'm going to use the addition rule for logs. You should be familiar with it. It's this rule here, where if you've got the log of two things being multiplied together, say x and y in base n, same as log of x in base n, plus the log of y in base n. So if I use that rule here, then I can express this as the log of a in base 10 plus the log of t to the power b in base 10. Next, I need to look at this term here, and I'm going to use the power rule for logs. Again, you should be familiar with this one. And that is, as a reminder, if you've got, say, the log of x to the power p in base n, it's the same as p times the log of x in base n. I just bring this power to the front of the log. And I can use that rule here. I can bring the b to the front of the log of t in base 10. If I do that, then I get this line here. Okay, so this is looking like what we have to show here. I'm just going to swap these two terms around though if it's to be exactly correct. And then I can compare this to what we've got to show. It's identical to m log of t in base 10 plus c, where m clearly relates to that b there, and c is the same as the log of a in base 10. Okay? Okay, for this part of the question then, we've got to find n when t equals 3. And obviously we can't find it straight away because we just don't know the values of a and b. But we did find out from the previous part of the question that we were able to express this equation in this form here. And this form is very useful, especially when we've got this graph here, because it's got the form y equals mx plus c. You can see that for the y-axis we're replacing it with the log of n in base 10, and for the x-axis we're replacing x with the log in base 10 of t. So that means that b is given by the gradient, and the log of a in base 10 is given as the intercept here. So if we know then that b represents the gradient and the log of a in base 10 represents the intercept, we can get b very easily just by looking at that gradient and drawing a triangle. I've chosen this triangle. The bigger the triangle, the better your chances of getting a good estimate, okay? And I've chosen then to take these 2 points here on the straight line. And we should be familiar with getting gradient. It's the difference in the y values, that will give us this distance here, divided by the difference in the x values, that's that distance there. So to get this distance up here, I just need to get the y values, and reading them off, I can see that we have 4.55 here and 1.85 there. And as for the x values, this starts at 0 and this value here is 1.2. So to work out the gradient then, difference in y divided by the difference in x, I get 4.55, take away 1.85, that's the difference in y, divided by the difference in x, 1.2 minus 0. If you work that out, you get a gradient of 2.25, and that's our value of b. Okay, we just need to find a next, and that, I said, was the intercept. And we can see that the intercept is at 1.85. So that means that the log of a in base 10 must be 1.85. And to get a, I just take the inverse of this. That would be that a is equal to the base, that's base 10, raised to the power 1.85. You should be familiar with that result. Now you could work this out, but I'm not going to. I'm just going to leave it as that value. And now I'm in a position to work out the value of n when t equals 3. It's just a question of substituting t equals 3 in here and our values for a and b. So you would get this sum here. And if you work this out, you'll find that you get 838.53 and so on. And if you give it to, say, one significant figure, it's 800. Leave it up to you, okay? If you gave it, say, to two significant figures, it's going to be 840. Three significant figures, 839. Okay, so, but I'm just going to leave it as 800 to one significant figures. Okay, so I hope that's given you some idea on how to do that. Okay, so if n equals 1 million, then why is it going to be unreliable to use this graph to find the value of t? And the reason is that if we look at this axis here, where we've got the log of n in base 10, I would need to find out what value I would need to look up on this scale in order to work out the value of t. So I would know then that to do that, the log of 1 million in base 10 is equal to 6. Got a problem, because the highest value that we've recorded here is 4.5, not 6. We're assuming, if we were to carry on, that this line carries on up here, and we would take our value of 6, let's say it's there, look across here, down here, and onto this scale here. But you can see it's not necessarily going to give us the right result. This graph, as I say, we're assuming it's a straight line. It might go off in that direction. It might in fact go off in that direction afterwards. So it's going to be an unreliable result, purely because we cannot extrapolate beyond what this graph is. And I've summarized that in this statement here, that since the log of n in base 10, this axis here, only has a maximum reading of 4.5, then we cannot extrapolate beyond this value, as it may be unreliable. Okay? Now, for this last part of the question, to say what the meaning of A is, we can get this by looking at the equation that we've got here. If we were to set t equal to 1, what we end up with is that n equals a times 1 to the power b. Now, 1 raised to the power b, raised to anything, is always going to be 1. So what we end up with is n equals a times 1, n equals simply a. So we see from this then that when t equals 1, n equals a, and that must mean that a represents the number of microbes after 1 day of the experiment. Okay? Okay, so for this question then, we're given these parametric equations for the curve C and asked to find out dy by dx. So in order to do that, you're going to need to use the chain rule. And you should already be familiar with it. As a quick reminder, remember dy by dx is equal to dy by dt times dt by dx. Or you can think of it as dy by dt divided by dx by dt. So first of all then, let's start with dx by dt. So we've therefore got dx by dt, and if we differentiate the variable cos t, You should be familiar with this result. It's minus sine t. So you've got the constant multiplying with that gives us minus 2 sine t. And when it comes to differentiating the cos 2t here, that's going to be minus 2 sine 2t. Again, you should be familiar with that result. So if you multiply it with the root 3, we get that dy by dt equals minus 2 root 3 times sine of 2t. So we now need to just get dy by dx, and I'm going to go for this division version. So that's just going to be dy by dt over dx by dt. So this result divided by that one. And so if you do that, you're going to get this. Okay? Now, I notice that the negative 2's cancel one another out, so I'm going to cancel those out. And we can work with the sine 2t. You should already be familiar with this identity here. Sine 2a is identical to 2 sine a cos a. So the a is really this t now. So I could write that then as root 3 times the 2 sine t cos t in place of sine 2t. And that's divided by the sine t. And what I can see now is that this sine t here cancels out with the sine t there. So what I'm left with is 2 root 3 cos t. And that's our result. Okay? Okay, for this part of the question then, we've got to find the equation of the normal to this curve C at the point P where t equals 2 pi upon 3. Now, in order to appreciate this, I find it easier just to draw a sketch. And when I say a sketch, this is not necessarily representative of this curve here. I've just drawn some squiggly line, and I've drawn my normal to this line at the point P, where t equals 2 pi upon 3. It just gives me an idea of what I've got to do. If I'm to get the equation of L, then I'm going to be looking at the form of a line, and that line has this form: y minus y1 equals m, the gradient, times x minus x1. And that will give me the equation of L. The problem is I don't know the gradient of L, and I don't know a point on that line with coordinates x1, y1. Well, I don't know those at the moment, but that's what we've got to find out. Now I can get the gradient of L very easily just by working out the gradient of the tangent at the point P. I get that by looking at dy by dx and substituting t equals 2 pi upon 3 into the equation. That will give me the gradient of the tangent then at P. And then I can use the perpendicular gradient rule to get the gradient of L. Remember, that perpendicular gradient is the negative reciprocal of the gradient here. And once I've got that, I also need a point on the line for our x1, y1 coordinates, and I can get that by substituting t equals 2 pi upon 3 into these two equations up here to give me that point. So I'm going to be working out the xy coordinates at P to give me x1, y1. So there's the method. So let's get started. Okay, so we need to get that gradient of the tangent. We've already found out from the previous part of the question that dy by dx was equal to 2 root 3 cosine t. So I just need to substitute my value of t equaling 2 pi upon 3 into here. Cosine of 2 pi upon 3 turns out to be minus a half. So if you put that in there, you're going to end up with minus root 3 for the gradient of the tangent then at P. So using the perpendicular gradient rule, the negative reciprocal of that gradient, we're going to have then the gradient of L is going to be equal to 1 over root 3. Now we need our coordinates at P, and I just need to substitute t equals 2 pi upon 3 into here to get the x coordinate. The cosine of 2 pi upon 3 is going to be negative a half. So you're going to end up with 2 times negative a half, and that's going to give you minus 1. So already you can see that this sketch is no way accurate. The x coordinate here is clearly a positive value, not negative 1. As for the y coordinate, again just substitute t equals 2 pi upon 3 into here. If you do that, you're going to get root 3 times the cosine of 4 pi upon 3. Remember, I double the value of t. Work that out, you've got root 3 times minus a half, and that's going to give you minus root 3 upon 2. So we've got our coordinates now, we've got our gradient of L, so we should be able to get the equation of L. So I'm just going to remove this method now, and so we're in a position to say that the equation of L is y minus y1, the y coordinate there, equals the gradient 1 over root 3 times x minus x1, negative 1 there. Okay? Now I'm going to multiply through by 2 root 3. If I do that, we end up with this line here. And then if I rearrange this by subtracting the 2 root 3y and the 3 from both sides, then rearranging it gives me this form here. 2x minus 2 root 3y minus 1 equals 0. Okay? Now, please don't write in and say this sketch is not accurate. I know that. All it was is just to give us an idea, a feel for how we were going to tackle that problem. Okay, so in fact, what I'll do is I'm just going to remove that sketch to avoid that problem. Okay? Now for the last part of this question then, we've got to find out where this normal L cuts the curve again, C, at a point Q. Now in order to appreciate this, again I've drawn another sketch. It's not an accurate sketch by any means. This curve that I've just drawn here, C, is not necessarily this curve here. So all I'm just trying to show you is that our normal L can cut the curve C at 2 points. And we've got to find this point Q then. So in order to do this, we have to use simultaneous equations as it's a point of intersection question. So what I'm going to do is number these equations at the top, 1 and 2, and the one here for L3. So if we number those equations, 1, 2 and 3, we need to solve them simultaneously. And the way you do this is you substitute 1 and 2 into equation 3. So if we do that, what we're going to get is this equation here. Next, I'm going to want to expand this and also pick up on this point here. We've got cosine t here and cosine 2t here. Remember, when you're doing trig equations, it's good to get them into the same trigonometric function. So I'm going to go for cosine t, not cosine 2t. We should be familiar with the expansion of cosine 2t. It's a double angle. It's the same as 2 cos squared t minus 1. So if you put that in and expand the brackets, you're going to get this. 2 times 2 gives us the 4 there, cos t. And here we've got minus 2 root 3 times that root 3 is going to be the minus 6. And I've replaced cosine 2t with 2 cos squared t minus 1. Okay, and there's that minus 1 equals 0 on the end. So I'm going to now expand this out. And if we expand that out, we're going to get this result here. Noticing it's leading towards a quadratic equation, I'm going to want to rearrange this and make this a positive term. So I'm going to multiply through by -1, and if we do that, you're going to get this quadratic equation here. And to solve this is a quadratic equation in cosine t. I could either use the quadratic formula or factorize it, because it does factorize. So if we factorize it, we get this line here. Now, because it's factorized, I can see that each of these factors would be equal to 0. And if this factor equals 0, cosine t would equal -1/2. And for this factor, if it equals 0, cosine t would equal 5/6. So we've got those values in there. Now, with cosine t equaling -1/2, this looks familiar, because if we were to take the inverse cosine to both sides, we would find that t equaled 2 pi over 3. And we realise that that's the value at P. So that means then at Q, cosine t must equal 5/6. Now I don't need to work out the value of t, because I can quite easily get cosine t just by substituting 5/6 in here in equation 1 to get our x coordinate of Q. So if you do that, you're going to get x equals 2 times 5/6, which leads to 5/3. Now when it comes to working out the y coordinate, we've got here cosine of 2t. But remember that cosine 2t, I showed you down here, is this identity, comes to 2 cos squared t minus 1. So we can see that y will equal √3 times 2 cos squared t minus 1. And at Q, knowing that cosine t equals 5/6, we can work out what y is just by substituting it into here. And if you work this out, you'll find you get 7/18 √3. And that leads us then to the coordinates of Q. The coordinates of Q are going to be 5/3, as we found up here, and 7/18 √3. Okay, now I'm just going to remove the sketch purely because it's not accurate and I don't want to mislead you. It was only there just to give us a feel for the question. So I hope that's given you some help on that question if you found any difficulty. Hi there. So nice question here where we've got to work out the area S, or give an estimate for the area of S using the trapezium rule. Now I'm assuming first of all you are familiar with the trapezium rule. If not, do go back and check out my earlier tutorials on this. But essentially what we've got to do then is to divide this up into strips, and those strips are going to have a width of half a unit. You can check it out by just looking at the difference between all your x values in the table. Okay, difference between 1 and 1.5 is 0.5. Same again between 1.5 and 2 is 0.5. So it's the width of a strip, 0.5. Remember, we always divide the width of the strip by 2. And then we multiply this result here with the first height, which is given by the y value for your first x value. So that's going to be 3. Then it's plus 2 times the sum of all the middle heights. That's the heights between x equals 1 and x equals 3. It's these 3 y values here. So we just need to put those in, 2.3041 plus 1.9242 plus 1.9089. Okay, so it's twice the sum of all the middle heights, and then we have to add to this the last height, which is this value here, 2.2958. 2.2958. And that is essentially the trapezium rule. Okay, width of a strip divided by 2, all multiplied with the first height plus twice the sum of all the middle heights plus the last height. Dead easy. Okay, so if you work this out on your calculator, you should find that you end up with 4.39255. And if we give this to 3 decimal places, then the answer is 4.393. Okay, to 3 decimal places, 3 dp for short. Hi there. So for this part of the question then, we're asked, how can we get a better estimate for this area S using the trapezium rule than what we achieved in the first part? Well, all we need to do is increase the number of strips, and we can do that by decreasing the width of the strip. Remember, the strip width has to remain the same though. So what I'd want to do then is take more strips by decreasing the width, and that should give us a better estimate for that area S. Okay? Now for this part of the question then, we had to work out the exact value of this area S here and give it in the form a over b plus the natural log of c, where a, b and c were integers to be found. So how do we do this? Well, we should know that to get an exact area here, we need to integrate the equation of the curve, y here, with respect to x between the limits x equals 1 and x equals 3. So if we put that up, okay, we should have that the area S is equal to the integral of y, okay, with respect to x between the limits 1 and 3. And obviously I've replaced y with what we're given here in terms of x. Okay, so having got that, let's just remove this graph here, give us a bit more room. We now have to integrate each of these 3 terms. Now to integrate this first term here, because I've got a product of 2 functions of x, x squared times the natural log of x, I'm going to be using integration by parts. And I'm also going to take this division by 3 out the front and see that as multiplying x squared natural log of x with a third. It makes the integral a lot easier to work with. So I'm assuming that you're familiar with integration by parts. If not, do check out my video tutorials on this, but here's the formula for integrating by parts. And if you've watched those tutorials, you'll know that when you're integrating something with a natural log of x in, then that part is the u part, okay? And that means that x squared here is the dv dx part. I'll just write it over here as a reminder, okay? So we've got u is the natural log of x and dv by dx is equal to the x squared. Okay, so when I'm working with this, I'm going to pull this dividing by 3 out as 1/3 times x squared times the natural log of x. It's going to make the integral a lot easier to work with. So just put a square bracket up here first of all, and we'll pull that 1/3 out. So all I'm doing now is concentrating on integrating x squared times natural log of x by using integrating by parts. So I'll put a bracket up here. We'll have one of these squiggly ones, okay? So using the formula then, okay, we've got the u part, okay, which is going to be natural log of x. So pop that in there, put it in brackets as well. Natural log of x multiplied by v. V is the integral of x squared with respect to x, and that will be x cubed over 3. Remember, we add 1 to the power and divide by that new power. Now I've got minus the integral of v. V being this part here, okay, the integral of dv by dx. So just copy down x cubed over 3, and then we multiply this with du dx. We differentiate u, which is now natural log of x, with respect to x, and get 1 over x, a standard result that you should already be familiar with. And we integrate this with respect to x. And then I'm going to finish off that bracket there. So we've got 1/3 then times all of this lot. So that's the integral of this starting to go forward, okay? Now, if I look at this term here, minus 2x, integrating that with respect to x, add 1 to the power, so you'll get x to the power 2, and divide by the new power 2, okay? For a constant, in this case 5, you just put an x behind it, so it's 5x. And I'll just square this off with the brackets, and we've got our limits here between 1 and 3, okay? And what I'll do now is I'll just remove that formula so that we've got more room to move on. And what I want to do next is just clean this up. We'll have our square bracket here first of all, and I'm going to multiply through by the 1/3. So 1/3 times x cubed over 3 is going to give me x cubed over 9, and then we've got that multiplied with the natural log of x. And for this one, remember we've got 1/3 times the result here. Well, I can see that we're going to have 1/3 times this third here. That's going to be minus 1/9 when I take into account that negative sign there. And I'm going to pull that out the front of the integral being a constant. It'll make it a lot easier to work with. And then I've got x cubed divided by that x there is just going to give me x squared. And that's integrated with respect to x. Okay? And cleaning up this term here, the 2's cancel, just leaving me with minus x squared. And then we got the 5x on the end. And we'll square off that bracket there and put our limits in between x equals 1 and x equals 3. Next, just going to clean this up a bit further by working out that integral here. So we've got x cubed then over 9 times the natural log of x, and when it comes to integrating x squared with respect to x, that's going to be x cubed over 3 times it with a negative 1/9, and you're going to end up with minus x cubed over 27. Okay, and then we've got minus x squared here and the plus 5x, and we'll put our limits back in between x equals 1 and x equals 3. All right, now let's start substituting our limits in. We'll put the 3 in first of all, so we've got 3 cubed, which is going to be 27, divided by 9, that's going to give me 3, and we've got the natural log of 3, okay, 3 times the natural log of 3. Putting 3 into this term gives us 3 cubed, which is 27, divided by 27, that's going to come out as negative 1 there. And then we got minus 3 squared, which is 9, so minus 9, and then 5 3s are 15. And I'll put that all in one set of brackets. And from this, we have to subtract what we get when we put 1 through. Now I can see immediately here the natural log of 1, that's going to be 0. So 0 times anything here is going to be 0. I'll just put 0 there. Put 1 into this term, we get minus 1/27. And then we got minus 1 here and plus 5 there. Okay, minus 1 and plus 5. Right, let's tidy this up now, and we're trying to head down to this format here. So I can see that if we just look at concentrating on the non-natural log terms, so I've got 15 minus 10 here, that's going to be 5. And I can see here I've got minus 1 out of 5, that's 4. Then that becomes minus 4. So I've got 5 minus 4, which is 1, and then I've got plus 1 27th. So 1 whole 1 is 27 27ths. Add another 27th to that, and that's going to give me 28 27ths. Okay, so that's my fraction. Now I've got to look at the natural log terms. So I've got just that 3 natural log of 3. And I can use the power rule here. I can see this as being the natural log of 3 all raised to the power of 3. Should be familiar with that rule there. So that's the natural log of 3 to the power 3. And I can see I'm getting there now because this is going to be equal to 28 over 27 plus the natural log of 3 cubed, which is 27. And you can see I've broken it down to this form here. If we're to give the value of A, it's going to be 28, the value of B would be 27, and the value of C would be 27. Okay? Hi there. Now for this question then, we were given this curve y equals f of x, and it had this equation f of x equals 4 sine 2x all divided by e to the power root 2x minus 1. It is just root 2, not root 2 of x, so it's root 2 times the x and then minus 1. And we had to show that the x coordinates of the maximum point P and the minimum point Q were satisfied by this equation tan 2x equals root 2. Now I'm going to take you slowly through this solution, but some of you might want to fast forward to the end and you'll see all the working. Okay? Now, in order to find out max and min points, what we need to do is realize that the gradient at the point P and Q is 0. So we need to differentiate this equation with respect to x and make it equal to 0. And then if we solve that equation, hopefully it will take us down to tan 2x equals root 2. Now, when it comes to differentiating this, we've got two functions of x being divided by one another, so we've got to use the quotient rule. And I'm assuming that you're familiar with the quotient rule. If not, do go back and check out my video tutorials on that. Okay, now I'm going to remove this graph here because it's just going to be in the way, so just take that out. So when it comes to differentiating this with respect to x, we'll put that as f dash x or f prime x as some of you might call it. Okay, the first differential of f of x with respect to x. So when it comes to using the quotient rule then, we take the denominator, in this case e to the power of root 2 multiplied with the x minus 1. So we take the bottom of the fraction, I'll put that in brackets, and we multiply it by the differential of the top. So we need to differentiate 4 sine 2x with respect to x. And for this, you should know the result straight off. It's going to be 8 cosine 2x, but we do it by the chain rule. And the chain rule, remember, is basically dy dx equals dy by dt times dt dx. It's as if these dt's cancel, leaving you with dy by dx. So for 4 sine 2x, if we were to let y equal 4 sine 2x and t equal the 2x here, you'd get y equaling 4 sine t. And so we need to do dy by dt first of all, and if you differentiate 4 sine t with respect to t, you're going to get 4 cosine t. And we fill the t in with the value 2x. So we end up with dy dt equaling 4 cos 2x. And next we need to do dt by dx, and if you differentiate t with respect to x, we've got t equaling 2x here. Differentiate it with respect to x, you just get 2. So dy by dx is to multiply those two results together, 4 cos t, or I should say 4 cos 2x, with the 2. So you're going to get 8 cosine 2x. So just pop that in there then as 8 times cosine of 2x. As I say, you should be able to differentiate that really straight off and get this result here, but otherwise the slow approach then is to break it down like this using the chain rule. So back to the quotient rule. Remember, it's the bottom of the fraction times the differential of the top, which we've just done, and then it's minus, and we do it the other way round. We take the top of the fraction, which is 4 sine 2x, and we now multiply it by the differential of the bottom of the fraction, the denominator. And again, to differentiate this, we would use the chain rule. I would let t equal the root 2x minus 1. So it'd have y equals essentially e to the power t here. And if you differentiate e to the power t, you get e to the power t. So that would be e to the power t, t being the root of 2 times the x minus 1. And then we multiply it by the differential of what we called t. The differential of root 2x minus 1 with respect to x would just be root 2. So I'll put that in there as root 2. So I'm showing you how I would differentiate that using the chain rule just off the top of my head. But I'll take you through that one more time. Chain rule then, dy dx equals dy dt, dt dx. I let y equal e to the root 2x minus 1, and t is the root 2x minus 1. So I've got y equals e to the power t. I differentiate y with respect to t, so I differentiate e to the t with respect to t, and I get e to the t. And replacing t with the root 2x minus 1 as we had here, you get dy dt equals e to the power root 2x minus 1. Then we need to do dt dx, differentiate t with respect to x up here, and you just get root 2. So all I'm doing is multiplying these two results together to give me essentially the differential of e to the power root 2x minus 1. And there it is up there. Okay, so we're still with the quotient rule. We now put all of this result over the denominator squared. So as I say, do check the quotient rule out if you're unfamiliar with it. Okay, I've got some tutorials on that. So we take the denominator, e to the power root 2x minus 1, and we square it. Okay. Now I'm going to clean this up. What I notice is that I've got e to the power root 2x minus 1 as a common factor on the top, and so I can divide it out with one of these results here. Okay, I've got that squared, so I can just divide through by e to the power root 2x minus 1. That will cancel, and I can take it out here, okay, as it's a factor of that. Now we can just tidy this up, and we've got 8 cosine of 2x, and then for this one we've got minus 4 times that root 2, so that'll be minus 4 root 2, and then the sine of 2x, and all of this is over e to the power root 2 x minus 1. Okay, now this gives us the gradient at any point on the curve. We're looking for the maximum and minimum points, and we know that that's when the gradient, which is given by f dash x or f prime x, equals 0. So that's going to therefore mean that if we put this equal to 0, just the top of the fraction would equal 0. Okay, 0 divided by this denominator here would give us 0. So that means that 8 cosine of 2x minus 4 root 2 sine 2x must equal 0. And it's just a question of rearranging this. Remember that the tan of 2x is the same as sine 2x over cosine 2x. So that's giving me a clue to what I have to do here. I'm just going to divide through both sides by 4. I can see that if I cancel that out, that goes once, that goes twice. Okay. And then if I add root 2 sine 2x to both sides, I end up with 2 cosine of 2x equals root 2 sine 2x. And now if I divide both sides by root 2 and cosine 2x, I end up with 2 divided by root 2 equals sine 2x over cosine 2x. And from this, we should see that sine 2x over cosine 2x then is tan of 2x, and root 2 will go into 2 root 2 times. So it follows that we get this result here. Okay? Hi there. Now for this next part of the question, remember we were given this curve then, y equals f of x, and it had these 2 points here, P and Q, a maximum here at P and a minimum at Q. And the x-coordinates of P and Q were shown to be given by this equation here, tan 2x equals root 2. Now for this question then, we've got to give the x-coordinates of the minimum point for y equals f of 2x and also for 3 minus 2f of x. Now what I'm going to do is take you slowly through this solution as always, but you might want to fast forward where you'll see the full solution at the end of the video. Okay, so going back to this question, first of all, what we need to do is establish the x-coordinates of the stationary points for P and Q, and then we'll be able to take it further for these 2 parts here. Okay, so we need to solve this equation, tan 2x equals root 2. So the next step would be to take the inverse tan to both sides, and that would leave us with 2x equals the inverse tan of root 2. And we need to find our solutions for this. And so what I'm going to do is turn to a quadrant diagram. So just draw that in here. This will be 0 radians, and we would turn anti-clockwise to get our solutions. And for the tan of an angle to be positive, we're taking positive root 2 here. Tan is always positive in the first quadrant, so just mark a line in there. And in the third quadrant, so mark a line down there, making sure that this line here is equally inclined to this horizontal line here. So these 2 angles would be exactly the same. And I'd mark in that starting from 0 here, turning anti-clockwise, then this angle here, which corresponds to this blue angle here, we'll call 2x. That will be one possible solution. And the other one will be to turn from here all the way round anti-clockwise until we hit the line again here. So this will be another solution, which we'll call 2x. Now, if you get on your calculator, make sure you're in radians mode. You'll find that if you take the inverse tan of root 2, you'll get 0.553 and so on radians. And that corresponds to this blue angle in here. Okay, we'll just mark it in here as 0.9553 and so on radians. Okay. So that gives us our first value for 2x. 2x equals 0.9553 and so on radians. And then we need this other possible solution, the one in green for 2x. So all we've got to do is carry on half a turn. In radians, that's the equivalent of pi radians. So if I add pi to 0.9553 and so on, you should get your second answer, which will come out, I'll just put or here, as 4.0969 and so on. Okay? Now I need to divide both of these answers by 2 to give me x. So we therefore have x equals, and dividing 0.9553 by 2, you end up with 0.4776 and so on. And if you divide 4.0969 by 2, you end up with 2.048 and so on. Okay? So these correspond to the x coordinates of P and Q. And P obviously is this first coordinate, okay, so that's the x coordinate of P, and 2.048, because it's greater than that value, corresponds to the x coordinate of Q. Now that we've established the x coordinates of P and Q, when it comes to looking at this graph here, y equals f of 2x, we've got to be familiar with transformations of graphs. And what this does to any graph is it causes it to stretch by a scale factor of 1/2 parallel to the x-axis, with the y-axis being invariant. So if you were to sketch that, you're going to get a graph that looks something like this, okay? This point here, Q, has been pushed up, if you like. It's the distance to the y-axis has been halved. So that's the point that we're interested in here, this minimum point here. And so all we need to do is take the x-coordinate of Q and divide it by 2. So I'll just put in here that therefore the min, okay, at x, okay, equals 1.024. I've just divided this result by 2. And if I round this to, say, 3 significant figures, we're going to get 1.02 to 3 SF, 3 significant figures. Okay? Now when it comes to this next graph, I'm going to break this down, okay? We're just going to take our original graph, y equals f of x, and if I put a 2 in the front of it, what that does is it stretches the graph by a scale factor of 2 parallel to the y-axis, with the x-axis being invariant. So what you're going to get is a graph looking like this, okay? Y equals 2 f of x. The point P has been pulled out by a factor of 2 here, and the point Q, the minimum point Q on y equals f of x, is pulled down by a scale factor of 2. Alright? Now when I put a negative in the front of this, minus 2f of x, the minus causes a graph to be reflected in the x-axis. So I'm looking at reflecting the green graph here in the x-axis, and you're going to get a graph looking something like this. So the minimum point now becomes the maximum point that was up here. That was the point P. And you'll notice it's all in line here, so the x-coordinate of this point down here is the same as the x-coordinate of P. So that's the graph of y equals minus 2 f of x. Now putting a 3 at the front here just causes this graph to be. So if I was to sketch that in, maybe it's going to look something like this, okay? I'm not too sure what 3 units is going to look like on this scale, but what I do see is that this minimum point here corresponds to the x-coordinate that we had at P, okay? So therefore I can use that result then and just say that the minimum point here at x, okay, is going to be 0.478 to 3 significant figures. It's the same as the x coordinate of P that we found up here.